Hi, I'm Michael Galley, and today I'm going to demonstrate the measurement of a single channel fiber bread grating using the virtual reference analyzer. The grating has two FC-APC connectors on both sides of it. So what we have is we have an FC-APC connector, FC-APC to FC-PC hybrid patch cord, so that we get the first reflection, because the FC-PC connector is going to be the first reflection point and the grating is going to be the second reflection point. There's roughly about 25 centimeters between the grating and the first reflection point, so that's an important fact here. It's within the 80 centimeter device length limit here. We're using it in reflection, so that's one of the limits there. So that's our connection. The grating is at around 1555 nanometers. Our scan is going to start at 1530 and go to 1570, and we do that because we want to be on the linear portion of the scan. When a laser tunes, it starts tuning and accelerates. So we want to be on the linear portion of the scan. So we're in the laser, or the grating is within the bandwidth, is at the center of the bandwidth approximately. So to start the scan, simply we've got our 1530 is the start wavelength, stop wavelength is 1570. We've connected to the proper GPIB port. You can always pull down the menu, hit refresh, and then select it'll automatically detect where your laser is. So what's important here is we're using for this particular measurement, we need to use one of the newer lasers. That's actually an important point. When using the VRA to measure narrowband devices, we can only use the 81600B series tunable lasers because they have a good linearity. So I guess let's go back to the measurement here. The number of points, we've got 50 points. Just leave it at the default. There's no compression. We're not using compression in this experiment, so we leave it at 1. And we're using a bulk reflecting element, so we put a check mark there because the grating itself is a bulk reflector. So that's one important fact to note. So once we're ready to scan, hit scan. And when you hear a tick, that means the laser's started its scan. It takes about 10 seconds, and you'll see the raw scan pattern. Once we have the reflection spectrum, we need to remove the bandwidth on both sides of the reflection spectrum, and the reason for that is that there's noise there. So we're going to isolate around the 3 dB points, or let's say the full width at half maximum of the grating. We need to remove any points beyond that. So I'm gonna show you here. You might be able to see it on the screen, so that you can see what to do here and learn how to use it. So we want to make sure that we've got the grating. Press OK, and you should see a power spectrum with nothing at 0 at the DC. So we've got a single peak. We're already balanced because the largest peak or valley is actually inside the spectrum. What you get is you get a big peak or valley at the center, and then you've got smaller peaks, or peaks with smaller periods on both sides. Okay, and we're talking about peaks of the envelope here. There is a carrier underneath. You can probably make that out. So since we're balanced, we're just going to press OK. We only have one peak and one valley for every, or we've only located one peak and one valley for every peak and valley. So we want to make sure that we don't have an X crossing with one of the X should be always above the green line. That's why we have this in that's the way we've set it up. So that's how it's done. So let's push OK, and the system will take over and produce the result. And again, in the second segment of this video, we'll do the screen capture